Hello friends, in this video we will study the two important terms which are used in 8085 microprocessor. They are stack and subroutine. Stack is a type of memory locations which are specified in the memory of 8085, and subroutine, it is a part of the program which is written at a different memory location. So stack and subroutine, they are frequently used in 8085 programming. So let's start with our topic. First we will study the stack. So what is a stack? A stack is a group of memory locations in the rewritable memory that is used for temporary storage of binary information during the execution of a program. So we write, whenever we write a program in the microprocessor, it is stored in the memory of the microprocessor. So that main program, if in the main program, if we have temporary results and for temporary storage of any type of binary data, we can have stack. So stack, it is a group of memory locations like 10 memory locations, 20, 15, any type of group of memory location will be called as stack. And this stack is used for the temporary storage of binary information. Now where we have this stack is in the rewritable memory of the processor. So because stack, it is a group of memory locations, so we have to specify the starting of the stack and the ending of the stack, like where the stack is ending, from where the memory locations are starting, and up till where it will going to end. So the starting of the stack, so we have to define the starting memory location of the stack and the end memory location of the stack. Now the starting memory location, it is defined in the main program. In the main program we have a pointer, stack pointer, and in the stack pointer we initialize the stack. The starting memory location will be given in the stack. Now in the stack, the storage of the binary data, it is done in the decrementing order. So we use the highest memory location which is available to us. So suppose we have the maximum memory location available to us is F, F, F and F. This is the memory address of the last memory location. So we are going to initialize the stack at this memory location so that all the memory locations above it, they can be used for the temporary storage of data. And when we are initializing the stack, we will do it in the main program. In the main program, we will write the instruction and initialize the stack pointer with this memory location, and through this we are defining the beginning of the stack to the microprocessor, and then the temporary storage will start at the memory locations below it. Now why it is called stack? Why this name is given to it, that group of memory locations is giving the name stack. This group of memory location is called stack because the contents of each memory location, they are stacked over one another, that is put over one another, and the information is retrieved starting from the top. So if we like represent it, these are the memory locations in the microprocessor. Now this memory location, it is the last FFFF. Okay, and we have initialized the stack from this location. So all the information which is being stored in this stack, it will start from this. So in this way all the information is stored in it, and when we want to retrieve it, it will start from the top. So one above the other, the memory locations are being put, and then the information is retrieved from the stack. That is why this name is given to this group of memory location as stack. Okay, now the beginning, it is specified in the main program, and we are initializing this stack pointer. So this beginning of the stack, it is defined in the main program using the instruction LXISP. So what this instruction is doing, this instruction is initializing the stack pointer or loading a 16-bit number into the stack pointer. So in this stack pointer, the 16-bit address will be loaded, and that denotes the beginning of the stack pointer, stack. Okay. Now when the information, it is getting stored in the stack, I have drawn the diagram of the memory locations. Suppose we have initialized the stack pointer here. We have stored all the informations in it. First it will come to this location, then second, then third, fourth. In this way all the memory locations will be, all the data will be stored. So this is how the storage in the stack is done. Now if we want to retrieve the information, retrieve this binary data, then 4 will first come out, then third, then second, then 1. So this is what last time which is entered into the stack, that is last in, will be the first to get out. So first out. So which technique is used in the stack? Last in, first out, that is LIFO technique. So the storage and retrieval of binary data on the stack, they follow the last in, first out, or we can say LIFO. L for last, I for in, F for first, and O for out. So this LIFO sequence is followed for the storage and retrieval of binary data in the stack. So once the stack is initialized, the storing of the data bytes, it begins at one memory location less than the address in the stack pointer. How we are initializing the stack? We are having this instruction LXI SP and the 16-bit address. So at this 16-bit address, the stack is initialized. Let's take an example. Like we have initialized the stack at 2099H. That means we have written in the main program the instruction LXISP and then we have written 2099H. So stack is initialized at this position. If we draw it, it will be, this is 2099 and here we have the stack pointer beginning. Now if we want to store the binary data in this stack, then one memory location less than this initialization, that means 2098, there that data will be stored. Suppose we are storing 08, this number we want to store. So this number will store at 2098. Again we want to store 07, then it will be stored at 2097, where we have 07, then one less than that. So in this way, the storage of data, it will begin at one memory address less than the address in the stack pointer. In stack pointer we have 2099, so storage will begin at 2098. Okay, that is why whenever we want to initialize the stack pointer or we want to initialize the stack, it is initialized at the highest memory location, because in decreasing order of the stack of the memory locations, the storage is beginning. So data bytes in the register pairs of the microprocessor, they can be stored on the stack in reverse order, that is in decreasing memory location. We can store the data bytes in the stack. Like if we have initialized the stack at the memory location 2099 and we want to store the BC register pair, so it will be stored in the decreasing order of the memory location 2098 and 2097, and two locations at a time, we are using because we are storing a register pair. Now at every location we can store an 8 bits and a register pair BC, it is of 16 bits. So 88 bits in half we are storing the data bytes, and we are using the instruction push for that. For storage we are using push, and for retrieving, that if we want to retrieve this data from the stack, then we are using the instruction pop. When we are using pop, we are increasing the memory location, incrementing it. First we are having 2097, then we will get 2098, and when we are storing, we are decrementing the memory location 2098, then 2097, and always two at a time when we are having the register pair. So let's study these two instructions, push and pop, the instructions which are used in the stack. So first instruction is LXI SP. This instruction is used to load the 16-bit memory address in the stack pointer for the initialization of stack. Okay. Next instruction is push. push, and we can push either a register pair or the program status word. Program status word is also the flag register. So flag register can also be its contents can also be stored into the stack. So what it is doing, the stack pointer So in this push instruction, what we are doing, the stack pointer is first decremented because it is being initialized at the 16-bit address. So it will be decremented once. Then the contents of the higher order register, we have B, C, D, E, H, L. These are the registers pair. So B, D and H, these are the higher order registers. So the contents of the higher order register, they are stored at that memory location. Again, that stack pointer is decremented and the lower order register is copied. Okay, so in this way the register pair can be stored. Also the program status word, its content, because it is an 8-bit register, so its contents can also be stored into the stack. Now if we have pop, then for pop also we have register pair and PSW. In this case, the stack pointer is incremented. Okay, stack pointer is going to be first the data byte is retrieved. So for pop, the contents of the memory location, they are copied into the lower order address, and then the stack pointer is incremented, and then again the contents are copied into the higher order register, and again the stack pointer is incremented. So let's take an example so that you can clearly understand. If you see that in this LXI, SP, push, pop, only the contents are copied. The contents of the source register, they are not altered, they remains the same, but the contents of the destination, they are only changed. So these are only the copying instruction, no transfer is there. Now let's take an example. So we have these three instructions. Let's see how the microprocessor is going to execute it. First is LXI SP2099. So the stack pointer, it is initialized at the memory location 2099. Then we have LXI H42F2. So in the HL register pair, we will have 42 and F2H. Okay, then push H. So this stack pointer, it will be decremented. That means its content will be 2098. Now here the higher order address register, that is H, will be stored. So we will have 42. Then this stack pointer, it is again decremented. So here we will have 2097 and the lower order address will be stored. Register will be stored here. So we will have F2. Contents will remain the same, just they are copied into the stack. Now next instruction, let's take another example here. So this is another example. Here we have initialized the stack pointer at 2400. This is the memory location 2400 and here the stack pointer is being initialized. Now LXI edge 2150H. So in the HL register pair, we will have 2150. Then we have LXI B 2280. So in the BC register pair, we will have 2280. Then move A, comma M. M means the memory location which the HL register pair is pointing. So this memory location is 2150. So suppose at this location 2150 some data is being stored. Suppose it's 08. So that data will be moved into the accumulator. So contents of accumulator are 08. Okay. Now we have to push H. The contents of the HL register pair has to be stored in this stack pointer. So it will be decremented by 1. So here we will have 23FF. Okay. So we first the higher order register, that is H, will be stored. Then lower order register 50 will be stored here. So this is 23FF. Then we have 23FE. This decrement you can perform like you have 2400. First convert it in the binary form and then -1. Do it. So you will get 23FF. Okay. So we have stored the HL register pair into the stack. Then push B. So again this will be decremented. This will be 23FD. And first B register will be stored, that is 22. Then C register, that is 80, will be stored here. And this address is 23FC. Now we have push PSW, that is the program status word will be pushed here. Now program status word, it is, here we have the flags register, which is the 8-bit flag register, and here we have the accumulator. If you see the programming model of 8085, then you will see that accumulator and flag register, they are combinedly the program status word. So this will be stored into here. So first accumulator will be stored and then the flag register will be stored here. So if there are questions based on the stack that after execution of these instructions, what will be the position of stack pointer, what is the contents of these registers, so you can solve the questions based on this. You know that whenever there is a push or pop instruction, then how the stack pointer is incremented or decremented. So this is 23FC, this will be 23FB, and this is 23FA. So after execution of all these instructions, the contents of stack pointer, it is 23FA. Okay. After execution of all the instructions. So this was the first topic which we studied in this, which we are studying here is stack. In stack, it is a group of memory locations which is used for temporary storage of data, and we studied 3 instructions which are used in the stack: LXI, SP, push and pop. Now second topic of this video is subroutines. So let's study about the subroutines. Subroutine name is given to it that it is a subprogram. We can say that main program is what we have written in the memory of the processor, and subroutine, we can say that another name for it is a subprogram, a short task which is to be repeated in the main program several times. It has been written at certain other memory location, and that program is called in the main program whenever that task has to be performed. So subroutine, we can say that there is a long program where subtraction has to be performed several times. So for subtraction, we have written a short program which will be called as subroutine. This subroutine is the subtraction program. And that program is called in our main program whenever subtraction has to be performed in it, because this main program, it is supposed involving the subtraction of two numbers 15 times. Now every 15 times you are writing the subtraction instruction and 4-5 instructions for that program again and again, so it is requiring a very large space. So instead of writing it again and again and getting tired up for it, we are writing a subroutine which is having all the instructions for the subtraction operation, and this subroutine is called in the main program whenever we want to perform the task of the subtraction. Okay, now in subroutines we have two instructions which are used in the subroutines. First is call and second is return. The mnemonic for this return instruction is RET, and for call instruction this is simple CALL, call. Now the opcode is a 16-bit address, and the opcode for return is none. So we write call, a 16-bit address is given here, and at that 16-bit address will be the location where the subroutine is written. So like suppose we have LXIH and 2050H, and we have MOV A, M, and we have written here call 2060H. And at 2060 memory location we have written certain instructions like MVI C05H, then decrement this C register, and then jump on, we have written here RET. This is for decrementing the C register. So we are calling a subroutine which is written at different memory location, and that subroutine we have written the last instruction as return. So when this instruction DCR is executed, when it comes to return, it will again come to the main program and execute further instructions. Okay, so this is how a subroutine is called, and return instruction they are used. So subroutine, it is mainly used to lessen up the space which is used to store larger programs. So it helps in this, and by using these two instructions, call and return, we can use the subroutines in the 8085. So in this video we studied about the stack and subroutine, how they are used in the 8085 programming, and I hope this video is clear to you. Thank you.